before we actually compute the expected value of xk, the number of marked marbles in the box at time k, let's go through the transition probabilities. We got a little bit of a hint of that in the previous clip, right? We saw that we started x0 equals 0, then the next transition happens with probability 1 to x of 1 is equal to 1. And then we saw that the first sort of randomness enters at time step 2, where we either stay at 1 or go up to 2. So you kind of, if you think about this, like what's going to happen over time, well, clearly this xk process is going to be, first of all, it's not going to decrease. Right? It's going to keep going up and up and up and up from 1 to 2 to 3, but it may not do it on every single time step. And so our first kind of goal is going to be to establish these transition probabilities, and sort of by doing so, we'll demonstrate that xk is in fact a Markov chain. So let's go through that. So what do we need to show if something is a Markov chain? You need to show that the probability of a future time step, given the history, right, the past, the entire past of the process, depends only on the previous step, right, xk, right? So that's essentially, if we can conclude that probability there depends only on xk, the previous step, you know that x is a Markov chain. So, we kind of thought through the transitions in the beginning, from 0 to 1, from 1 to 2. Let's think about x as denoting, our present state. Right? So little x is going to be the number of marked marbles in the box. And we're going to first list, what I would encourage you to do is, before jumping into the probabilities, list what are the possible events. And so we saw that when x was 0, the next transition had to be just precisely 1. But after that we had some randomness, and so if you think in general, once we'll let time run a little bit longer here, and you'll see a number of these marbles get marked. What's going to be this? What's going to be the set of possibilities here from x? What's the transition, right? So what you want to do is list these and then assign probabilities to them. So if we have x marked marbles at any point in time, you can either stay at x again, which corresponds to which event? The one where we pick a marble that's already marked, or x plus 1, which corresponds to picking an unmarked marble. And the next, so once you're sure of these, what are called transitions, once you're sure you have these right, then you want to assign them probability. So WP means with probability. And you kind of want to sit here and you can kind of try to write out some examples if you have any trouble. But the reasoning here goes as follows, right? If we had x marked marbles in the box and we transition to x, what event does this correspond to? It corresponds to the event of something that's already marked being picked. What's the probability in this case of picking out something that's already marked? Well, it's going to be, right here it's 4 out of however many n, right? And if we start with x, right, it's the same thing. What's the probability of picking a marked marble when there are x marked? It's x over n. And right away here, you can kind of say, well, these are the only two possible outcomes. So the probability that we go up by 1 is going to be 1 minus this, right? And if you want to argue it a little bit more carefully, or a little bit more from sort of first principles, then you say, well, what event does this correspond to? Well, this, what happens is that we pick something unmarked, and we marked it, right? That's the way to go up, to increase the count up by 1. And so what must have happened is that we had to pick an unmarked marble. How many of them are there? Well, there are n minus x unmarked marbles over n total possible equally likely choices. And so now you have this transition with probabilities together, and now you can go back to here, right, and write out what this is, right? So at least to go up here, right, what are the possible choices? Well, this is there are going to be two choices, right? And y is going to be either going to be equal to either xk, right? Xk is going to be the current state, and we know that the other potential is y is equal to xk plus 1, right? So these are the possible transitions, right? These are the two possible values for the chain x at the next time step. And now here we want to put in these probabilities. So what are they? Well, looking directly from here, right, you can just substitute, right? If xk is playing the role of little x here, right, and so this one is just xk over n, and this one is n minus xk over n, right? And these are sort of the corresponding to the two events, right? And so you see right away that this depends only on x, right? And therefore, right, so right from this statement here, right, from this little exercise, you conclude that x, right, there's an implication, is a Markov chain. Right? In other words, all that had to be illustrated was that these what are called transition probabilities depend not on the entire history of the process, but only on the current time step. And these, right, this path of the process, right, these set of outcomes that happened way back in history, just don't matter, right? They don't enter into this calculation. So at this point, we know that x is a Markov chain. We now know, because of this, that a first step transition analysis is possible to carry out, and the way to start that transition analysis is through, the Tower property, right, of conditional expectation. So let's try to see if we can write that down. And this is exactly what you would be doing on homework 1, right? You start out with the expectation that you're trying to compute. Then the next, your next step is to condition on, well, rather, let's just make it even easier because our transition probabilities are written in terms of k plus 1. Let's just compute this expectation. So your first step is to what's called condition on the current time, and the current time is xk, or condition on the previous step, right, where this is the next step, right? K plus 1 is the next time. We want to condition on time k, and so I will write this, right? So this first move here is justified by the Tower property of conditional expectation, right? And now all you need to do is you can evaluate this expectation in terms of the two probabilities, right? And then here it's asking what are the possible outcomes, right? The possible outcomes were y either stays at xk or it goes up by 1. So I know that this expectation is going to be equal to xk times the probability, the conditional probability that xk plus 1 is equal to xk given xk, right? That's the first conditional probability, plus the other outcome, which was xk plus 1, right? We increase the number of marked marbles in the box, and this is the probability that xk plus 1 is equal to xk plus 1 conditional on xk again. Right, and if you're not comfortable with having these sort of random quantities in your conditional, that's okay. So first of all, this is perfectly legitimate to write, but if more comfortable, you could just replace them with little x. So I could, for example, replace all of these symbols here with the following maybe slightly more basic notation, which is x is the value, right, of this right entire integrand, right? This is the thing in the expectation, and I'm saying, well, it's going to be either x when this probability is met, namely when xk is equal to x, and the other outcome was little x plus 1, when this was equal to little x, right? And I can also remove the random quantities here, right? And so this is another way of writing the very same thing. Okay. And now what I can do is substitute the actual values of these, and we know what they are. They're right here. And so this one was x over n, and this one was n minus x over n. And now at this point you just start simplifying, right? This one simplifies to x squared over n. And now we can write what this one out, what this one is, right? This one is going to add on x plus 1. This is for multiplying this part by the 1 minus x, and then there is this part left. Right, hopefully I got that right. I think there's a minus sign here. Right? And so now you'll see that, for example, right, this x squared is going to cancel with this one. So this is going to cancel this x. And the only thing that's left is a minus x over n. Right? And this part is gone. Right? So I keep reducing this and keep reducing this until I get to 1 plus x. Looks to me like it's 1 minus 1 over n. And now we're essentially in a position to get a recurrence,